Good afternoon, everyone. I'm Hsien-Ming. First, I have to apologize in advance that I'm not having hearing aid with me, and for government bureaucracy reason, I'm not going to have a hearing aid for hardly another month, so I cannot hear your questions. So if you have any question, you can try. You can try write on your cell phone and show it to me, or speak louder, or ask our chairperson, Dr. G, or like Professor Lincoln Hui to help me to repeat your question. All right, so today I'm going to talk about using light responsive biofactors to help your experiments. Sorry. So this picture actually is the central idea of today's talk. We have an important biomolecule that we want to be activate at a certain time or location. We use light. So you will hear me say cage the molecule, cage biofactor, cage protein a lot. So the cage is showing here. So this cage will release your bioactive molecule only after you are irradiated by light. All right, so when I was 6 years old, Dr. Hoffman, his group come up with the idea. That is to adding this orthonitrophenzyl group on ATP, so that way they can control the reaction using ATP as a reactant. So for example, this kinase, if it needs the ATP, when it sees this, you won't be able to use it until we photolytically remove this. All right, so I think he was trying to use this to control the ion channel activity. So that was the first case, the reaction in a scientific community. So that was the first one, cage the ATP using as a reactant or energy source. But if you really think about this, why is this too messy? Because you probably, more people know this than me. It's that ATP is involved in so many reactions in the cell biology. So if you use this cage ATP, you actually will affect so many biological pathways, and you won't be able to get a clean, controlled reaction that you want. So what does people want? I think when people using cage molecule to do experiment, what they really want is they want to gain exclusive control of a reaction that is in a certain intended pathway. So if you are using a small molecule that is too upstream, it's not a good choice. How about cage the substrate? Well, cage substrate is too downstream, because unless your substrate has a further biological function, otherwise you cannot use the cage substrate to control the upstream enzyme, to control the signal transduction pathway or whatever the pathway that you want to control. So, and then chemists start thinking about, well, you know what, maybe we can do a cage inhibitor, because inhibitor is very specific towards a certain enzyme, right? So if we can use a cage inhibitor, or we can stop the enzyme activity until the moment we photolytically destroy the inhibitor. Well, that is a very good thinking, but it's very difficult to make. Because of this, no matter what good inhibitor you have, right? If you want to make a photoresponsive version of that, you're going to inevitably has to install a photoresponsive unit into the inhibitor. That very likely will kill the activity of the inhibitor, right? So that's also, it's not a dead end, but it's just difficult to make. Unless your peptide or unless your inhibitor is a bivalent type and there's a linker in between. But that way you can probably easily accommodate this. So this whole field has changed direction to cage protein. Well, cage protein is very laborious because you need to structure information, and you also need molecular biology to do some point mutation if needed. And you also need to have a scale of protein chemistry. Well, protein chemistry, when just hearing it, you don't know what's the difficulties lies underneath this. Because if you are a good organic chemist, you will think that the chemistry are relatively easy. But actually, it's not, because all the chemistry has to be in an aqueous solution. And it's very likely that your chemistry will work, but you kill the protein activity. So that's where the difficulties of protein chemistry. All right, so I'm going to give in today's talk stepwise by showing a different application from simple to complex, but it's not through the date of the publication. All right, so the first one is a very simple one. What I did when I was a postdoc is trying to develop a system where I can control the release of a certain cargo from certain suborganelle of a cell to the cytosol. And the release will be reported to us visually by fluorescence. So the probe was designed this way, and this probe is concentrated on the mitochondria. So in this case, if the photolytic event occurred, the cargo release, and you will report to us. So you can see that in this case, the cell is treated with this probe, but without light signal, the release doesn't happen because there's no fluorescence reporting to us. Here's the irradiating light spot. You can see that it's showing fluorescence light. So it tells us the cargo has been released. And you can see that this cell is very long shaped. The mitochondria here is not fluorescent. So it tells us that the spatial control actually worked. Only under the light spot, the cargo has been released. Here is not. You can see that here we also have a mitochondria. This one is the channel of the mito tracker. This one is our caged peptide. So that was the simple release version. And this one is a little bit more complicated. Back in 90s, people can using a simple organic chemical reaction to modify protein kinase A. What I'm doing here right now is a much more complex version because first, the electrophilic reaction that I use is a chemoselective. We have two cysteine here, but only this cysteine will get reactive, not this one inside the active site, because this one is affinity ligand directed. And it also has this visual fluorescence reporting mechanism design in it. So we have a fluorophore and a quencher. So if the photolytic event happens, it will show us fluorescence enhancement. So you can see that here is the native pKa, and when we throw in the peptide, it will dock to the active site this way. And this middle group, which is the electrophile, will be in the right location to react with cysteine 343. And after that, this protein is no longer having activity, but short irradiation of UV light will cleave this photolabile linker to free this inhibitor, and this protein will become active again. And not only just that, now the protein is reporting strong fluorescence. So you know from the fluorescence microscope that this protein is activated. So from the microscope, you can see that this is the inactive state of the pKa. The fluorescence is really dark, but here is the activated after activation. The fluorescence is very strong, and you can see that the pKa actually activated the stress fiber rearrangement pathway. So the cell is losing its normal morphology because the cytoskeleton collapsed. So that's this work. And one downside of this reaction is you have to use UV light. A lot of people doesn't like the short wavelengths of light. So in this work, I use something called upconversion nanoparticle, where it's composed by lanthanide ion. It has this special effect where, like, you can do a organic compound UV absorption, UV experiment, you will see the energy gap is rather big, huge. So you need a strong wavelength light to excite that, short wavelength light to excite that. But when it involved to a transition metal, you can see the excitation wavelengths start getting longer, require less energy. When it comes to lanthanide ions, it has the F orbital, so the near IR photons can driven the electron excitation. So the electron in the F orbital keep climbing up, and eventually it's gonna relax to the ground state. But at this time, it's relaxing all the energy absorbed from IR photon and then released at once. So it's generating UV light. So that way we can activate the pathway. And this one is a very recent work. The beauty of this is we can use blue light instead of electrophilic chemistry to conjugate the peptide to the protein in living cells, because it's very chemoselective, because this photo-induced electron transfer reaction requires very, very short distance, so it won't react with other off-target protein. We also try to use this upconversion nanoparticle to conjugate to the channel rhodopsin. So the channel rhodopsin that can see the blue light now can be activated by near IR light also. All right, so Joseph now, he's a neuron chemist trying to solve the problem. He wants to use the TDP43 to study the amyloidogenesis of the, you want to observe that inside a living cell. But what he encountered is the problem that he doesn't have a tool to start all the protein aggregation from time zero. So I tell him that we can try this. So we generate these peptides having 8-arginine. So that way this peptide is not in an aggregation prone state, but after the light irradiation, it can certainly aggregate to form this. So he successfully used that to demonstrate that TDP43 can be generated, the aggregation can be generated inside the living cell. And this work is actually a very good example showing how a biologist, cell biologist, and chemist work together. This was Professor John Condilis and my postdoc professor David Lawrence. They collaborate on this work. John Condilis is a cell biologist. He knows how important covalent is, how covalent can rearrange the actin fiber by this pathway. And he knows the structure and important residue, but he doesn't have the capability to generate a covalent that's under our control. So he talked to my professor, David Lawrence, and David told him, if you want to chemically modify this protein, then serine is not a good choice because alcohol is not very reactive. You have to change this to a point mutation to cysteine. But that way you are risking losing the activity of the protein. So they did the experiment, the mutation actually works well, the protein is still alive. So then they using this orthonitrophenol group to cage the cysteine side chain. Now the protein become inactive. And then they inject this cage protein into the cell and use a laser spot to irradiate the cell location. And you can see that the direction between irradiation and the direction of moving, there's an angle, right? If you do the cosine theta of this angle, if this cosine theta is close to 1, it shows the strongest positive correlation. Where you irradiate, the cell will moving towards that direction. If the cosine theta is a -1, it tells you wherever you irradiate, the cell moving towards the totally opposite direction. So they noticed that within first 6 minutes of irradiation, the cell is moving towards the where you irradiated. Also, that's the end of my talk. I want to end my talk by having Dr. Kronberg's remark. He said, basically he's saying this, 我们已经闯进银行了，可是我们那个分子生物学已经让我们闯进银行了，可是我们手上没有化学工具去打开保险箱。That's basically what happened. I think it's also true at this time. So it's a good timing that we can having a good collaboration between physicists, biologists, and chemists. Okay, so that's the end of my talk. Thank you very much.